We were discussing about the problem of starting large induction motor from direct full voltage supply, and then the solutions were that for wound rotor motor you better connect a resistance in the rotor circuit, terminals are available. But however, for cage induction motor, which is very popular and widely used, that thing is not possible. So, you have to adopt a reduced voltage starting, of which we have discussed reactor starting. You have to connect a reactance in line with the series, and then auto transformer. You have to connect an auto transformer at the very beginning. This was reactor starting. Only thing I leave it to you to try to understand. Even if it is wound rotor induction motor, you could apply it. I mean, no problem. If it is wound rotor induction motor, rotor shorted, you could adopt any of this method. But since wound rotor motor, that facility is there, you can do like this. Similarly, auto transformer starting, but you have to see your motor operation now depends on another equipment of same rating. So, cost is pretty high, because you have to of course go up to this point when the motor will be running. After machine has started, picked up speed, it has got close to synchronous speed. Then of course, by doing a switching here, you can give the supply corresponding to rated voltage. That arrangement can be done. But only thing is, these things can be avoided, and a start delta starter can be used, provided that motor is meant for delta connected rated condition operation. Otherwise, it is not possible, and not only that, all the terminals of the stator must be brought out. We will later see that nowadays the induction motor can be very soft started by using electronic inverters. I will also tell while discussing the speed control of induction motor. So, first, speed control of induction motor, various methods which were earlier used, no point in discussing in detail, but I will give you definitely the idea. For example, so next topic is speed control. See, for any motor, three things are important. One is the starting. How do you start the motor? Always any motor, full voltage if you apply at the time of starting, it draws large current, be it DC motor or AC motors like that. So, some starting arrangement is to be made. Similarly, how the speed of the motor can be controlled. Okay, this is another. And third one is braking, electrical braking, that is if you want to bring a already running machine to come to stop quickly, what electrical arrangement can be made or done. So, about the speed control, the problem is clear, because suppose you have an induction motor whose torque slip characteristics is suppose like this, and this side is speed. You understand that, and this is slip. I have for the first time drawn it like this, reversed, but it does not matter. This is the starting torque. So, speed is 0 here and speed is ns here, and slip, S is 0 here, S is 1 here. So, anyway, this is the induction motor speed, and motor operates in the stable zone. This is almost a linear portion, and we have discussed that. Suppose there is a load torque, full load torque will be in between this about 5%, this value I told you about 10%, for estimation. So, suppose this is full load torque, and this full load torque I want to supply at various speeds. Mind you, from no load, in no load frictional torque it was operating here, full load it has come here, and there is a change in speed, but this is not called speed control, it is speed regulation, inherent speed regulation of the motor. So, it must run at lesser speed so as to develop more induced voltage in the rotor, more current, etc., more power. So, this is speed regulation from no load speed to full load speed. This by the term speed control I mean that if this is the load torque, can this load torque can be supplied at various other speeds, like this speed is close to synchronous, can I make it run at a speed ns by 2 close to that, then it is speed control. Okay, same load torque I am supplying. The answer is yes, whatever we have learned so far it can be done. For example, if it is slip ring induction motor, it can be only done with a slip ring induction motor, control rotor resistance, control external rotor resistance, to control speed. You know, if you vary the rotor resistance, we know the speed torque characteristics will shift. It will be like this, R2 increasing this way, R2 external increasing, and you can get a, from the same torque slip characteristics you can get a thing like that. Why not more like this, different values you can get, and you can easily see that is in the rotor of the machine, stator supply you give, and on the rotor slip ring and brush I am not drawing, you are connecting the resistance and varying this resistance, and you will find it may operate then at this speed, it may then operate at this speed, it may then operate if this load torque is like this, it will operate here. Stable zone, these are stable zones, mind you. Only thing you have extended the rotor resistance. Therefore, smooth variation of the speed of the motor can be achieved provided you increase this rotor resistance and down to a very low speed. So, I was telling the other day, if on the nameplate of the rating of the machine some speed is written, that is the full load speed, okay, that is this speed. However, if it is needed, you can run it at much lower speed in the stable zone. For various reasons, speed control is required, you can understand, but only point is, only objection to this method is there will be excessive power loss because of the presence of the external resistance in the rotor circuit, and this resistance I am not using only for the starting purpose. I want to control the speed, so resistance must be present in the rotor circuit as well, and therefore, rotor current will flow as you load the machine, TFL is there, therefore, there will be huge copper loss in the rotor and efficiency of the whole system is down. So, although a smooth speed control is possible, it is not very much used nowadays, it is not used at all. I am telling you, but the idea is like this. Similarly, earlier days people used to also tell that speed control by controlling the supply voltage. I will control the supply voltage and hence get different operating speed. For example, this is the inherent torque slip characteristics with V rated voltage, and this is the, suppose the load torque is here. You reduce the voltage, and if you make the supply voltage half, then the maximum torque will become 1/4. So, it will be like this. The slip at which maximum torque occurs here in this case will remain same, and therefore, it will become like this, and it will become like this. For B applied, you are reducing. B supply is B rated, B supply you are decreasing. Various families of curve you will get, and you will say, okay, it was running at this speed, now it will run here, it will run here, like that. But this is also see, over a very limited range you can control the speed, that is one thing. And second thing is, if the load torque is constant, the game will be over. If you further reduce the voltage, machine will come to stop, your motor will not be able to produce torque in this way. Perhaps still people say, why they say is because of the fact, if see, I am drawing load torque constant demand, this is the torque speed characteristics of the load in the red line I have drawn. But if the torque slip characteristics, it need not be the demand of the speed torque characteristics is like that, it could be this way. Suppose this is the load torque, and this side, mind you, this is Ns and this is Nr equal to 0. If the load torque characteristics like this, that is the load torque demand increases if you reduce the speed, then also okay, this method may be able to sustain. It will operate here, it will operate here. That is the torque demand at lesser voltages are lesser. So, this, although the speed will be very limited, it cannot be motor cannot be made to run at a very low RPM, these days are over. So, that is with slip ring induction motor. So, slip ring induction motor, rotor resistance is one option, supply voltage variation may be applied both to slip ring and cage rotor. And there were in earlier days methods, I will just mention verbally and tell you this story. Earlier days, because after all the synchronous speed decides the rotor speed to F by P. So, people used to have several stator windings or same stator windings connected for 2 poles or 4 poles by doing some external switching. Are you getting? One day I was explaining to you, same 3-phase winding, it can be made to appear as a 4-pole winding or a 2-pole winding by interchanging the connections of the different phase groups or coils like that. In that case, all the terminals are to be brought out from the machine, and then you want to operate as a 2-pole machine, connect the terminals in this way, If you want to operate at 4 pole machine, connect the terminals that way, so many terminals, then externally connect, then give supply. By doing that, you can at best get 2 discrete speed. Suppose you are changing the connection of the stator coils, whose terminals first of all you have brought out and made it connect to give you a 2 pole, which corresponds to 3000 rpm, and another for 4 pole, which corresponds to 1500 rpm, because motor after all will run at close to synchronous speed and below the synchronous speed. Therefore, there were complexities. Another thing was there, where people used to take 2 induction motors, which are mechanically coupled of 2 different number of poles, separate machines. One is of P1 poles, another is of P2 poles, and this motor could be connected in cascade. That is, the rotor of the first motor is used to supply the stator of the second motor. First motor should be a slip ring, second motor should be a cage, it could be a cage, and then those are nice interesting methods, no doubt. Then you could generate a synchronous speed of 2f by P1 plus minus P2, etc. 2 machines you have to use, and these 2 motors are coupled. It will, the common mechanical load will be on the shaft of the motor. So, by using pole changing method, pole changing method matlab the effective pole of the machine of the whole setup has you are changing. So, perhaps 1, 2, 3, 4 possible speeds are possible. One is 2f by P1, do not connect the second machine. Another is 2f by P2, first machine do not connect. Another is connect these 2 machine in cascade, that is, rotor of the first machine is used to supply the stator of the second machine, and depending upon the phase sequence of the supply of the second machine, P1 plus P2 or P1 minus P2 will come. Discrete speeds you could get, but nowadays no point in telling. To control the speed of an induction motor, you take another induction motor, not a good proposition in present day. Therefore, these we will not discuss. Although these are interesting, whoever first suggested must be very, intelligent persons to do that. The problems were elsewhere. The problem of induction motor, when you compare with DC motor in those days, induction motor requires a 3-phase supply, 3-phase supply is there, and the supply frequency was fixed 50 hertz. You cannot do anything with that frequency earlier days. In case of DC motor, you control the armature voltage, you control the field current by a simple rheostat. Smooth control of speed is possible, but with frequency fixed for a given induction motor whose stator connection you do not want to change, the synchronous speed is fixed 2f by P, and rotor speed will be simply very close to ns at steady state, that is all. And therefore, induction motors were considered to be almost a constant speed motor. People used to, one question which was very common even 10-15 years back, that in traction which motor is used? Series motor, DC series motor was the answer. Okay, nowadays also it is used, but the problem is nobody was talking about induction motor, whether speed could be controlled at ease with induction motor. We found whatever standard techniques were there, these are either efficient, inefficient techniques, cannot be used, or you require complicated winding terminals of the stators available to you, and that to discrete speeds only. Smooth speed train, you want to move at various speeds you like, starting from 0 speed to any speed you define. So nowadays, so the problem was because of because the synchronous speed is the deciding factor, which is 120 f by p in rpm, and f was 50 hertz constant. So, for a given machine, synchronous speed is constant, hence its rotor speed. Now, with the advent of power electronics inverters, that thing can be overcome, because you can easily see, to control Ns, why not control the supply frequency? Why you say only 50 hertz is available and do not do anything else? Therefore, I must have a device which will, but my existing supply available at my doorstep or in the lab is 50 hertz, that is the mother supply, I cannot do anything with that. So in block diagram it will be like this. This is your 3-phase supply 50 hertz, is there, and then motor I was connecting earlier, but now those days has gone. What you can do is this: you first convert it to a DC supply, use a rectifier, get DC, that I can do. Diode rectifiers, powered diode rectifiers are available, I will make it DC. Then whatever I will connect is a 3-phase inverter. Inverter, you know, with fast acting switches like MOSFET, transistor switches, it will give out a 3-phase source here, and there should be controls by which it will give you a output balanced 3-phase voltage source of variable voltage, variable frequency. I will just touch upon this idea. Ideas are so nice, that is why you must know. So it is DC here, have a very smart inverter which will give you a variable voltage, variable frequency output. Maybe I am just indicating it, it is suppose voltage control, there will be a knob, there is a frequency control. Okay. And I can then have any voltage, any frequency, a situation like this. If this thing is available and if this is your induction motor, be it cage, wound rotor, I do not mind now, do not care, rotor is cage suppose, and variable voltage, variable frequency supply, with that I will excite the machine. Then at least one thing is clear, okay, supply frequency can be controlled, number of poles I will not touch the winding, no point connecting another motor in cascade, no. So, like that we will do, and if frequency can be very smoothly controlled, speed too will be controlled. Before I talk, let us try to see what is going to happen. Suppose you have an induction motor. One thing of course very important to understand is only this much, that is, this is the stator, this is suppose the rotor. The motor has got a rated voltage and frequency, and if rated voltage and frequency is there, rated V rated, how it is related with frequency applied voltage, because that leakage impedance drop is negligibly small if you assume. So, this is nothing but 4.44 or root 2 pi f, then phi into then kW into N1 per phase voltage, per phase rated voltage. This is the basic equation. Suppose somebody says, okay, I will, and the rated frequency f rated is 50 hertz. Based on that rated voltage frequency, there is some rated flux I can calculate of the motor, and note that phi flux is V rated phase by 4.44 f and kW into N1. Now, kW N1 are constants, they are not changed, and here is this one. So, it is some constant into V rated phase by f. Suppose rated voltage is 400 volt, 50 hertz actual machine rating. I suppose decide, okay, I will run it at 400 volt, because inverter gives you variable voltage, variable frequency. I will adjust it to 400 volt and 25 hertz. I want to run it at half the rated speed. Suppose what, depending, suppose P equal to 4, rated speed is 1500 rpm, 50 hertz supply. Now, suppose I say, oh, if it is so easy, then apply rated voltage, but make frequency 25 hertz, it will give you 750 rpm, is not, or in between any frequency, reduced frequency 50 hertz down to 25 hertz, it will give you smooth speeds of synchronous values. But the problem will be there. What is that? If you keep the voltage fixed and go on reducing the frequency, then the phi will go up. Phi, as you know, it is 4 by P B max LR, that is B max will go up. And the motors or transformers are designed, if you look at the BH curve of the machine, which is not a straight line for its whole range of operation. So, this is H, or in other scale magnetizing current NIM by L something, and this rated flux density corresponding to phi rated, this is B, this is B rated. It is selected at the knee point of the machine. Based on that, it is designed. So, immediately I observe, if I keep the voltage same and frequency half, the level of flux required, this equation demands, flux density should be twice like this, and therefore, the current drawn will be very large. And in other words, people say the motor will get saturated. So, saturation is to be avoided. So, how this can then be avoided? Do not control the inverter which is supplying the motor. If you are varying the frequency in the lower range, make sure V by F, this ratio remains constant. That is, if it is a 400 volt 50 hertz machine, if you want to run it at synchronous speed corresponding to 25 hertz, that is your intention, then applied voltage should be also made 200 volt, so that flux level remains same. Understood? Therefore, it looks like that frequency, supply frequency, which is nowadays very easy to implement, should be the key word in controlling the speed of the induction motor. And also we will see that starting method we are using some auto transformer and reactor. Those things also will not be needed when you have a variable voltage, variable frequency supply. So, in the next class I will tell you about that. Okay, thank you.